Hello, my name is Joseph Ferrari, and this is my circuits lab report. The main goal of this lab was to predict circuit behavior and to learn how to measure current and voltage using multimeters. So, key concepts. Ohm's law states that the voltage across a circuit element is equal to the current multiplied by the resistance of that element. The total resistance of a circuit depends on how resistors are connected to each other. In series, the equivalent resistance is just the sum of the individual resistances. In parallel, the equivalent resistance is the reciprocal of the sum of the reciprocals of the individual resistances. The loop rule states that going around any closed loop in a circuit, the sum of the voltages will equal zero. The node rule states that any current entering a junction must also leave the junction, which is a statement of conservation of charge. Now, capacitors. While uncharged, the voltage of a capacitor is zero, and it has no resistance. However, as the charging process occurs, its voltage and resistance gradually increase until it acts like an infinite resistor in the circuit. Its voltage while discharging can be modeled by this equation, which can be linearized by isolating the exponential component and taking the natural log of the equation. The time constant, or R times C, of a capacitor basically gets across how long it takes to charge and discharge a capacitor. Just as a quick preview, in the experiment, we mainly determined that the charge and discharge times of a capacitor are equal when connected to the same resistors, and that current gradually decreases while charging and discharging the capacitor. So there were three main parts to this lab. Firstly, we set up a circuit to see the loop rule in action. We measured the voltage across each circuit element in the loop and then made a potential versus position graph. The second experiment involved a different circuit with a capacitor, in which the time in which it took to charge and discharge the capacitor was measured. The last experiment involved making a linear plot of the voltage of a capacitor against time while discharging a capacitor. So here's the setup. Basically, what was being measured was a property of was the system, while everything else in the circuit can be considered the surroundings. For example, if we were measuring the voltage across capacitor, the capacitor would be the system, while the battery and other resistors in the circuit would be the surroundings. So some assumptions include that all wires and batteries had no resistance, all ammeters had no resistance, and all voltmeters had infinite resistance. Otherwise, the math would have been a little more complicated. So in part one, we determine the voltage across each circuit element and then determine the resistance of each element using Ohm's law. Of particular importance, we see that the ammeter had no resistance. Also, we see that when measuring the voltage with a voltmeter, the current didn't change, which indicates that the voltmeter had infinite resistance. So here's some data tables for parts 2 and 3. The top one shows the time duration of charging and discharging a capacitor based on the initial resistance in the circuit. As you can see, the charging and discharging times were identical. The bottom table is my data for voltage of a capacitor and time while discharging a capacitor, which I use to make a graph that you'll see in a few seconds. Here's my plot of electric potential versus position from part 1 of the experiment. As you can see, the sum of the voltages add up to zero, which further validates the loop rule. Also, you can see that the batteries had positive voltage while resistors had negative voltage, and the wires and ammeter had no voltage. Here's my graph of the natural log of voltage over initial voltage against time. As you can see, this yields a linear relationship with a slope of negative 0.1662 per second. We can now use that slope value to calculate a value for the time constant of the capacitor used in the circuit in part 3. These calculations are shown on the right, where I isolate for the time constant RC. As you can see, the theoretical and calculated values are extremely close to each other. The percent error was calculated to be about 0.28%, indicating that there was very slight error involved in the data collection process. One possible source of error could be the imprecision of the ammeters and voltmeters in the PHYS simulation. Now, if I was doing this lab in real life, what would have changed with the ammeters? Well, in real life, ammeters have some resistance, which would have reduced the measured current of the circuit and changed some of my calculations. Now, if I used a real battery, what would happen with the capacitor if it was only connected to that battery and some wires? Well, according to my ideal model, this would result in a time constant of 0 seconds, meaning that the capacitor would reach full charge infinitely fast. Obviously, this isn't valid because in real life, batteries and wires have some resistance, because life is not an ideal simulation. In conclusion, ideally, ammeters have no resistance and voltmeters have infinite resistance, but in reality, this isn't true. Also, the rate at which a capacitor charges and discharges decreases over time. Lastly, assuming that batteries and wires have no resistance is only a valid assumption if there are other elements with such high resistances that the resistances of the batteries and wires can be considered negligible. Thank you.